Hey, Math 30-2s. Today we're going to look at rational equations. So a rational expression is the ratio or quotient of two polynomials, such as 3 over x plus 3. That's a rational expression. A rational equation is an equation, meaning it's got an equal sign, where at least one of the terms is a rational expression with a variable in the denominator. So here is an example of a rational equation. Here's another one. Both these have an equal sign, and at least one term is a rational expression. The process of solving a rational equation involves solving a linear or quadratic equation. Well, we know how to solve linear equations. That's pretty straightforward. We did that in grade 9 and 10. We're going to review the process of solving quadratic equations because we did that in grade 11. And we're going to do that before we solve any rational equations. So review, solving quad equations. X squared plus 5x minus 6 equals 0. It's a quadratic equation. If I look on the left side of this quadratic equation, I've got a simple trinomial because there's a 1 in front of the x squared term. The process of factoring a simple trinomial is to ask ourselves what two numbers have a sum of the middle term, 5, and a product of the last term, negative 6. So what two numbers multiply to negative 6 and add to 5? Well, that's 6 and negative 1. Well, if it's a simple trinomial, those are the factors of x squared plus 5x minus 6, x plus 6, and x minus 1. Now, x plus 6 times x minus 1 are the factors of the trinomial, but now it's an equation, so they equal 0. To solve the equation, I should set each factor equal to 0 then. X plus 6 can equal 0, or x minus 1 can equal 0. So either of those two factors can equal 0, and then I solve those very simple equations. Here x would equal negative 6, or here x would equal positive 1. So those are the solutions to this quadratic equation, negative 6 or positive 1. Part 2, I've got a complex trinomial. In other words, there's a number other than 1 in front of the x squared term, and I want to factor this complex trinomial before I can solve this quadratic equation. So to factor a complex trinomial, we ask ourselves what two numbers have a sum of the middle term, negative 11, and a product of the first times the last. 2 times 12 is 24. So the two numbers that add to negative 11 and multiply to positive 24 are negative 8 and negative 3. Back with a simple trinomial, when I found those two numbers, they were the factors, x plus 6, x minus 1. Not true in a complex trinomial. With a complex trinomial, I'm going to decompose the middle term. So instead of writing minus 11x there, I'm going to use those two numbers we just found, negative 8 and negative 3, and rewrite negative 11x as negative 8x and minus 3x. And I'm then going to factor by grouping. So I'm going to group the first two terms and look for the greatest common factor, which happens to be 2x. If I divide 2x out of 2x squared minus 8x, I get x minus 4. I factor the second two terms by grouping, so the greatest common factor of negative 3x and 12 is a negative 3. I divide both terms there by negative 3 and I get x minus 4. I notice now that x minus 4 is a common binomial to both these, so I factor out the x minus 4 and I'm left with 2x minus 3. I have now completely finished factoring the complex trinomial on the left side of this equation. I can now set either factor equal to 0, so x minus 4 can equal 0, or 2x minus 3 can equal 0. And I'm now going to solve these simple equations, so x could equal 4, or x could equal, I would add 3 and divide by 2. So x could equal 4, or x could equal 3 halves. Part B says verify the solutions using the intersection feature on our graphing calculator. So what I'm going to do is go to my graphing calculator. If I'm doing this first one on my graphing calculator, I'm going to let y1 equal the left side of this equation, and I'm going to let y2 equal the right side of this equation. I'm going to find the point of intersection between those two functions. So let's go to our graphing calculator and do that. Let's go to your y equals screen. Left side, x squared plus 5x minus 6 is y1. Right side, y2 is 0. Hit zoom 5, our standard, zoom 5 works, that's zoom square. We want to actually zoom 6, our standard viewing window. And we see y1 is a parabola, y2 is a line, which happens to be the x-axis. Second, calculate the intersection, number 5, of these. Just have to hit enter 3 times, and there's one of our solutions, x equals 1. Find the other solution. The second, calculate the point of intersection, hit enter twice, and you now want to make a guess closer to this other point of intersection, somewhere over here, and we notice that after we press enter is -6. So it satisfies by graphing x equals -6 and +1 for the first one. Beautiful. I'm going to do the same thing for the second one if you want. Go back to your calculator, go back to your y equals screen, and in y1, let's type in 2x squared minus 11x plus 12. In y2, let's let that equal the right side of the equation, which is 0. Graph it. We've already gone zoom 6, we just have to press graph. There is the left side of the equation, a parabola. The right side is the x-axis. Go second, calculate the point of intersection. Hit enter 3 times, and it'll give us one of the points of intersection, which is 1.5. And we said one of the solutions was 3/2, so that's the same thing. Do it again and find the other point of intersection. Second function, calculate number 5. Hit enter twice, and now move your cursor closer to that second point of intersection. Press enter, and we'll notice it's 4. So 1.5 and 4, yeah, that's what we had. 1.5 and 4 for the solutions for that second quadratic equation. So let's algebraically solve the following. They don't want us to do it graphically, they want us to algebraically solve these. So step 1 is to let the equation equal 0. So let's add 20 to both sides. And so now a simple trinomial, so we're going to factor this as 2 binomials. What two numbers add to -9 multiply to 20? Well, those are x minus 4 and x minus 5. And we now set each factor equal to 0 to solve this quadratic equation. So x would equal 4 or x would equal 5. There are our solutions. We could graph them to check, but those are going to be fine. Part B is a complex trinomial. So we ask ourselves, what two numbers have a sum of the middle term 13 and a product of the first times the last? 6 times -5 is -30. So what two numbers add to 13 multiply to -30? Well, those two numbers are 15 and -2. And the last question was a simple trinomial. Those two numbers were our factors, -4, -5. But now we're going to decompose that middle term using 15 and -2. So 6x squared doesn't change. Instead of 13x, I'm going to write plus 15x minus 2x. That's the same value. 15x minus 2x is 13x. And then I've got the -5 there, which equals 0. I now factor by grouping. The common factor of my first two terms is a 3x. Divide both terms by 3x, I get 2x plus 5. Look at my last two terms. The common factor there is only a -1. Divide both terms by -1, I get 2x plus 5. Remember, this is an equation, so it still equals 0. If I've done it properly, the binomial should be the same in both terms. In this case, it is 2x plus 5. So I factor that out. I'm left with 3x minus 1. And this whole thing equals 0. I can now set either factor equal to 0 to solve this equation. So 2x plus 5 could equal 0, or 3x minus 1 could equal 0. And solve those simple equations. So here x would equal, I would subtract 5 from both sides and then divide by 2. Or the second one, x would equal, I would add 1 to both sides and then divide by 3. So there are my solutions, -5/2 or +1/3. That's how we solve quadratic equations. All right. Now let's go solve some rational equations. There are several strategies for solving rational equations algebraically. Each of these strategies will result in a polynomial equation to be solved. We'll focus on rational equations whose solution depends on solving a linear or a quadratic equation. Since there are non-permissible values when dealing with rational expressions, we must always check that the solution to the linear or quadratic equation is not a non-permissible value. All right, we can't have a solution that's not permissible, so we always want to check those. We're going to focus on two types of strategies to solve rational equations: cross-multiplying and multiplying each term on both sides of the equation by the lowest common denominator. So either one of those two methods are going to work best for us. So solve a rational equation by cross-multiplication. If the equation consists of a single rational expression on each side, such as the one listed here, we use cross-multiplying to simplify the equation. This strategy has been used in previous courses when working with ratios. For example, 4 over x equals 2/3. If I want to solve this, I can cross-multiply and say 4 times 3 equals 2 times x. Simplify that, 12 equals 2x, or divide both sides by 2, x is 6. So in example 2, in each case, state the non-permissible value. Do that first. Solve the equation algebraically. Make sure the solution is true in the original equation, and make sure it's not a non-permissible value, and you can verify it on the graphing calculator. So let's do all these things. 3 over x plus 3 equals 6. Well, that's like saying equals 6 over 1. So if I cross multiply, I get 3 times 1 equals 6 times x plus 3. However, the first step we were supposed to do was state non-permissible values. So let's go back up here. There's the only variable in my denominator, so x can't equal -3. All right. Now I go ahead and cross multiply. 3 times 1 equals 6 times x plus 3. 3 times 1 is 3. 6 times x plus 3 is 6x plus 18. Solve this equation by minus 18 for both sides. So 3 minus 18 is a minus 15. That equals 6x. And divide both sides by 6. And we get x equals -15 over 6, or -5 over 2. All right. So that's our solution for x. We should now verify this by substituting that back into the original equation. So let's do a verification. Sometimes we call that a check. So let's do a quick check. So 3 over -5 halves plus 3. So 3 over -5 halves plus 3 should equal 6. 3 over -5 halves plus 3, if I want to add fractions, I need a common denominator. So 3 over 1 is the same as 6 over 2. That should equal 6. So I've got 3 over -5 halves plus 6 halves is 1/2. So 3 over a half should equal 6. Well, let's say 3 divided by half is like saying 3 times the reciprocal, 2 over 1. Well, that should equal 6. Yeah, 3 times 2 is 6, so it checks out. That was quite a bit of work to do an algebraic solution, algebraic check, but it did work out. Do a graphical check. Well, this one looks really crazy, so go to your graphing calculator. Go to your y equals screen. In the left side, type in 3 over x plus 3. 3 divided by, and be careful, my denominator has to be in brackets, x plus 3. On the right side, type in, in y2, type in the right side of the equation, which is 6. And now hit graph. There is the left side, 3 over x plus 3. Here's the right side, y equals 6. Find the point of intersection. So you go second calculate, number 5. Point of intersection, first curve, second curve. There's only one point of intersection that occurs right there at -5 halves, or negative 2.5. All right, so it checked out algebraically, it checked out graphically. This is a good solution. All right, it's also a permissible value because x can't equal negative 3. Well, this isn't negative 3, so that's good. If you go back to your graph, x can't equal negative 3 shows up right here. Here's negative 3. And look at that. That first part of our graph approaches that line, x equals negative 3, but never touches it. So that's called an asymptote on our graph. It's a non-permissible value in our expression and equation. All right, let's look at part B. 3 over x plus 3 equals 9 over 4x plus 7. Step 1, let's state some non-permissible values. X can't equal negative 3, or in this case, negative 7 divided by 4. Those are our two non-permissible values. All right. Now let's go ahead and let's just erase that. Now let's go ahead and cross multiply to simplify. Sorry, to solve this equation. So let's go ahead and cross multiply. 3 times 4x plus 7 equals 9 times x plus 3. All right. Expand that out. 12x plus 21 equals 9x plus 27. So in this case, I want to get all my variables on one side and my non-variables on the other. So I'm going to minus 9x from both sides. I'm going to minus 21 from both sides. So 12x take away 9x is 3x. 27 take away 21 is 6. Divide both sides by 3, and x equals 2. All right. Looks like a good solution. Let's check it. So let's do a quick verification. Plug 2 in for x. Everywhere I see an x, so 3 over 2 plus 3 should equal 9 over 4 times 2, which is 8 plus 7. 3 over 5 should equal 9 over 15. 3/5 the same as 9/15. Yes, it is. That checks out very nicely. So we know it works algebraically. We know it's a permissible value because if I go back up here and look, x is 2 looks like it's fine. Let's do a quick graphical check. So in y1, we type in 3 over x plus 3. Great, we've got that already. In y2, we should type in 9 over 4x plus 7. 9 divided by, make sure you put your denominator in brackets, 4x plus 7. Now hit graph, you get a couple interesting graphs. There's 3 over x plus 3. There's 9 over 4x plus 7. Our solution is supposed to be 2. All right. So if I go second calculate, point of intersection number 5. First curve, second curve, make a guess, don't have to. There's my solution, x equals 2. So it works graphically, we solved it, we checked it algebraically, checks out, so that should be a good solution. All right. Let's try example 3. Consider this rational equation. Rewrite the equation so that one term is on each side. Right? Because this thing equals 0, I could move everything to one side of the equation. I could move this to the other side of the equation. So 2x over x plus 2 could equal 0 plus 5 over x plus 3 is just going to be 5 over x plus 3. Now let's find the roots of this equation by cross multiplying. So once I'm in this situation where I've got one rational expression on each side of the equation, I can use cross multiplication. So let's state my non-permissible values first. X can't equal negative 2 or negative 3. Now let's do some cross multiplication. 2x times x plus 3 is the same as 5 times x plus 2. They're equal, right? 2x times x plus 3 equals 5 times x plus 2. Solve this equation, expand this out. 2x times x plus 3 is 2x squared. plus 6x. 5 times x plus 2 is 5x plus 10. Now that I've got a single equation without any denominators, I'm going to set this equation equal to 0. So I'm going to move everything to this side of the equation. I'm going to minus 5x, and I'm going to minus 10. And I'm going to get a quadratic equation on the left side. So I get 2x squared, 6x minus 5x is a plus x, and minus 10 equals 0. So I now have a complex trinomial on the left side of this quadratic equation. So I'm going to factor this, ask myself what two numbers have a sum of the middle term, which is 1, and a product of the first times the last. 2 times negative 10 is negative 20. What two numbers add to 1 multiplied to negative 20? Those two numbers are 5 and negative 4. So I'm going to decompose that middle term. So 2x squared plus 5x minus 4x minus 10 equals 0. So 5x minus 4x is the same as 1x, so I've changed the way this thing looks, but not the value of it. I now finish factoring by grouping. Common factor of 2x squared plus 5x is an x. That leaves me with 2x plus 5. Common factor of negative 4x minus 10 is a minus 2. Divide both terms by minus 2 and I get 2x plus 5. Whole thing equals 0. Well, I've done it correctly if I've got a common binomial factor. So I factor out that binomial of 2x plus 5, and I'm left with x minus 2. And that equals 0. Now, once I'm down to this form, I can let either factor equal 0. So 2x plus 5 can equal 0, or x minus 2 can equal 0. And those will be the solutions to the equation. So in this step, I'm going to minus 5 from both sides and then divide by 2. Over here, I'm going to add 2 to both sides. There are our solutions. We've solved it algebraically using cross multiplication. All right. You could check them with your calculator. You could plug them in and check them algebraically. Those are correct solutions. Example 4. Leo was solving the rational equation 1 over x minus 1 equals 4 over x squared minus x. His work is shown below. He cross multiplies. 1 times x squared minus x equals 4 times x minus 1. He expands it out. Looks good. Expands it out. He's done that correctly. Sets it equal to 0. Very nice. Factors that, and he gets x minus 1 and x minus 4 equals 0. Very nice. Sets each factor equal to 0, and he gets solutions of x equals 1 and x equals 4. However, his answer is incorrect. Where did he make a mistake? Well, the first thing we should do when we're solving a rational equation is to state non-permissible values. So you go back up to the original equation, we have to look at our denominators. X minus 1 can't equal 0, and x squared minus x can't equal 0. So here, x can't equal 1. And over here, let's factor. That's x times x minus 1 can't equal 0. So x can't equal 0 or 1. So I've got non-permissible values of x can't equal 1 or x can't equal 0. I go to my solution and it says x equals 1. But I notice that's a non-permissible value, so that should not be allowed. So the correct answer to Leo's work should only be x equals 4, as x equals 1 is a non-permissible value. If I were to try and check and see if x equals 1 works, if I plug it back into my original equation, I get 1 over 1 minus 1, which is 1 over 0. As soon as I divide by 0, it's undefined. So I can't ever get this equation to work when x is 1. So x is 1 can't be a good solution. It's a non-permissible value, doesn't work. The only good solution is x equals 4. All right. Note, although x equals 1 is a root, it's a non-permissible value. Solutions to rational equations must always be checked for extraneous roots. Those are called roots that don't work because of the restrictions. All right. So I'd like you guys to try questions 1 through 5, and then you come back and do lesson 8, part B. All right.